Welcome back. In this video, we'll go through sections 13.5 through 13.7. We're looking at conjugated systems in chapter 13. So now we're going to start to look at some real conjugated systems and start to get a better understanding of their structure. So alkadienes are simply called dienes, and polyunsaturated hydrocarbons, trienes, tetraenes, and so on, are extremely common in nature. They're extremely important to our everyday life. So butadiene, a common component for rubber. These are other dienes, hexadiene, cyclohexadiene. We'll see cyclohexadiene a lot when we talk about the Diels-Alder reaction later this chapter. You can have trienes. Notice it's alternating double bond, single bond, double bond, single bond, double bond. This is a conjugated system. We would expect carbon 2 all the way to carbon 7 to lie essentially in a plane. Actually, carbon 1 all the way to carbon 8 to lie essentially within a plane, because this is a planar carbon, so that must be in the same plane. So 1 to 8 would lie essentially in the same plane. We also have dienes, so we can have an ine conjugated to an ine. And then we can have enes, where there's both an ene and an ine in the molecule. And these systems are not conjugated. These are what we call isolated double bonds. Or we would say this double bond is isolated from this triple bond. Double bond is isolated from this triple bond. Cumulenes are a quirky class of molecules where instead of the double bonds being conjugated, we've brought them even closer together. So instead of alternating double bond, single bond, double bond, now we have double bond right next to another double bond. And you might think that makes it even more stable and gets more interaction between those double bonds, but actually it does the opposite. What happens is these p orbitals are no longer coplanar with each other. Each of these carbon atoms is sp hybrid. Well, excuse me, the central carbon atom is sp hybridized. So the central carbon atom has a carbon. Let me draw. There we go. Central atom has a carbon, and it wants to make a sigma bond in each direction. And then to make one of those pi bonds in one direction, we use a p orbital. And then to make the other pi bond in the other direction, we use a p orbital. So one of our pi bonds, the bond, let's say the bond going left, is using this up and down p orbital, and the bond going to the right might be using this other p orbital. Actually, I think the way they have it drawn, because these hydrogen atoms are coming at us and going away from us, it's the other way. So based on this drawing here, what they have is a central carbon we have p orbital overlapping with another p orbital. And since this p orbital is up and down, our hydrogen atoms must be going into and out of the plane of the page. Then I have my only p orbital that's left on the central carbon atom interacting with a p orbital on the leftmost carbon, and the hydrogen atoms therefore must be going perpendicular to that p orbital and above and below the plane. So you can see that these two hydrogen atoms on the left are in the plane of the page. These two hydrogen atoms on the right are out of the plane of the page. And these two molecules are actually enantiomers. They're actually non-superposable mirror images of each other, if you consider all the orbitals involved. All right. So cumulenes are less common. They are synthetically accessible. They're actually synthetically very useful for specific reactions, but they're much less common than conjugated and even non-conjugated dienes. Conjugated dienes are especially stable. We talked about conjugation and how we consider this a continuous molecular orbital going from one p orbital all the way to the other p orbital at the other end of the molecule. So it's a continuous network of overlap of orbitals. You can think of electrons being able to move freely from one end to the other of this conjugated system. Non-conjugated dienes or isolated dienes, we call them isolated because the electrons here are confined to this small region, and this pair of electrons is confined to this small region. Because there is no p orbital here available, there's no conjugation, there's no communication between this double bond, and this double bond. There's no additional stability for these two double bonds. So if we look at 1,3-butadiene, we can see that the bond lengths of the two double bonds are about 1.34 angstroms, and the central bond is about 1.47 angstroms. Bond lengths are really useful because they allow us to get some understanding of the hybridization state of the atoms involved. They allow us to get some understanding of how attracted to each other the atoms in question are. So a normal sp3 hybridized carbon bond, so two sp3 hybridized carbons bonding to each other, that's a 1.54 angstroms. So butane, that central bond, is 1.54 angstroms. If we make this carbon sp2 hybridized, then it goes down to 1.5 angstroms. And if we make one carbon sp hybridized, then it goes down to 1.46 angstroms. So you can see that as we add more p character to either one of those carbons, it's going to bring that bond length down. And there's a little bit of an extra factor in here due to that conjugation. There are two stable conformations of butadiene. There are essentially infinite conformations of butadiene. You're allowed to rotate this bond. But if we think about what we call the S-cis conformation and the S-trans conformation, this is not a cis conformation. A cis conformation, or cis, involves a double bond, which cannot rotate. This is S-cis. So cis versus S-cis. S-cis means that the sigma bond is in a cis-like conformation. That's what the S is for, S for sigma. So S-cis conformation has our two pi bonds on the same side of this molecule. The S-trans conformation has the two double bonds on opposite sides of the single bond, opposite sides of the molecule. And you can see that this S-trans conformation is going to be more stable than the S-cis conformation, the same way that a trans double bond was more stable. Whoops. The same way that a trans double bond was more stable than a cis double bond. And that has to do with the steric interaction of these hydrogen atoms, or whatever groups might be present here, as you bring these two bonds to the same face of the molecule. Long story short, S-trans conformation is more stable, and if you have 1,3-butadiene, it's going to exist in the S-trans conformation more often than it exists in the S-cis conformation, though it will exist in both over time. You expect free rotation around the central bond, and it will rotate over time to give you both conformations. It will just spend more time in the S-trans conformation. That becomes important when we start looking at the Diels-Alder reaction later this chapter. It becomes really important to think about whether or not a molecule can even adopt this S-cis conformation. 1,3-butadiene can. All right, so let's talk about molecular orbitals. We talked a little bit about that earlier. Molecular orbitals of 1,3-butadiene, going back to the structure of 1,3-butadiene. You see that we have 1, 2, 3, 4 sp2 hybridized carbons involved in the conjugated system. 1, 2, 3, 4 p orbitals involved in the conjugated system. That's these 4 p orbitals. Each p orbital would have 1 electron, total of 4 electrons in the pi system. So going from isolated p orbitals to molecular orbitals, we go from atomic orbitals to molecular orbitals. We start off by drawing the bonding orbital. The bonding molecular orbital has all the lobes in phase. Electrons can move freely all the way from one carbon on one end of the conjugated system to the other end. As we go up in energy, we increase the number of nodes in the system. Here we have one node right in the middle. Notice how we go from red to blue as we go across the top. So electrons are isolated to the left side or the right side of the molecule in this second molecular orbital. Third molecular orbital has 2 nodes. We have an isolated region on the left, a central region, and an isolated region on the right. And then finally, an antibonding orbital with 3 nodes, 4 completely isolated pockets for electrons to live. We say that we take these 4 orbitals, we put them into the lowest energy orbitals in the system, and we notice that all 4 of these electrons go from being at some energy to some lower energy level as a result of forming these molecular orbitals. So they go down in energy as they're allowed to move around more and more space, essentially. As you isolate them more and more onto a single atom, they go up in energy. Okay, so we have a system that's lower in energy than what we started with. Notice that we have our first two orbitals, our bonding molecular orbitals, are both occupied with electrons. We say that these two orbitals are occupied with electrons. If we look at this orbital, it's the highest energy orbital that is occupied by electrons. The highest occupied molecular orbital, or the HOMO. Highest occupied molecular orbital. If we go up to the next orbital, this is the lowest unoccupied molecular orbital, or the LUMO. Lowest unoccupied molecular orbital. So the HOMO and the LUMO end up being a really important place to focus our attention for conjugated systems. Because remember that in chemistry, we're always interested in the valence electrons. Those electrons that are the highest in energy and are most accessible for reactions. So this distance in energy between the HOMO and the LUMO ends up being really important. We'll talk about that when we talk about UV-vis spectroscopy. It's called the HOMO-LUMO gap. All right, stability of conjugated dienes. Conjugated dienes are more stable than you would expect for just two isolated double bonds. So if we look at two molecules of 1-butene and one molecule of 1,3-butadiene, and we look at the energy that comes out when we hydrogenate. So we hydrogenate, we get some energy release as we go downhill in energy, and here we get 254 kilojoules per mole. Here we get 239 kilojoules per mole. So a difference of 15 kilojoules per mole. What does that mean? That means that these two double bonds that were separated in separate molecules started out 15 kilojoules per mole higher in energy than this diene did. Started out higher in energy, meaning it's a higher energy structure. These double bonds are more energetic than these double bonds. The double bonds in the conjugated diene are more stable. That's the stability of conjugated dienes. So this is that information shown pictorially. If we take two molecules of 1-butene versus 1,3-butadiene, and we do the hydrogenation reaction, the two molecules of 1-butene go to give us butane, and we get 254 kilojoules per mole of energy. And if we look at hydrogenation of 1,3-butadiene, we use the same amount of hydrogen gas, we form butane. This time we get a lot less, or we get 15 kilojoules per mole less energy out of the system because it was that much closer to being as stable as butane. So we say that these conjugated dienes have additional stability relative to isolated double bonds. Okay, that's it for conjugated systems. Next time we'll start talking about ultraviolet visible spectroscopy, or UV-vis spectroscopy. And UV-vis spectroscopy is really going to focus on this HOMO-LUMO gap. So please try to remember that for next time. All right, I'll see you then.